Welcome to DAR Tutors. Today we will explore key quantitative chemistry concepts crucial for IB chemistry higher level. The topics we'll cover include stoichiometry and limiting reactants, percentage yield, and atom economy. By the end of this session, you will be able to perform calculations involving these principles and understand their significance in chemistry, especially in the context of green chemistry. Our first topic is limiting and excess reactants. This is a fundamental concept in chemical stoichiometry. In a chemical reaction, the limiting reactant is the substance that is completely used up first. Once it's consumed, the reaction stops. Conversely, the excess reactant is the substance that is not completely used up. After the reaction has gone to completion, some of it remains unreacted. It is crucial to understand that the limiting reactant dictates how much product can be formed. Just like baking cookies, if you have plenty of flour but only a few eggs, the eggs are the limiting ingredient, and the number of cookies you can bake depends entirely on how many eggs you have. Let's consider a simple chemical reaction, the synthesis of hydrogen chloride. The balanced equation shows that one molecule of hydrogen, HH, reacts with one molecule of chlorine, ClCl, to form two molecules of hydrogen chloride, HCl. This means they react in a 1:1 ratio. We'll explore this with three hypothetical experiments to build our intuition. In experiment 1, let's say we start with one molecule of hydrogen and one molecule of chlorine. Given the 1:1 ratio, they will react completely, leaving no H2 or Cl2. The products will be two molecules of hydrogen chloride. This is a perfect stoichiometric reaction, with nothing left over. Now for experiment 2. Suppose we have three molecules of hydrogen, but only one molecule of chlorine. Again, they react in a 1:1 ratio. One molecule of H2 reacts with the one available molecule of Cl2. This produces two molecules of HCl. We are left with two unreacted H2 molecules and no Cl2. In this scenario, chlorine is the limiting reactant because it ran out first. Hydrogen is the excess reactant, with two molecules remaining. Finally, experiment 3. Let's start with one molecule of hydrogen and two molecules of chlorine. This time, the one hydrogen molecule reacts with one of the chlorine molecules, forming two HCl molecules. We are left with no hydrogen but one unreacted chlorine molecule. Hydrogen is the limiting reactant, and chlorine is in excess. This illustrates that the amount of product is always determined by the reactant that gets used up first. So, how do we systematically identify the limiting reactant in a chemical problem? The key is to compare the mole ratio of the reactants you have to the mole ratio required by the balanced equation. A common tip for this involves dividing the amount of each reactant by its stoichiometric coefficient from the balanced equation. The reactant with the smallest resulting number is the limiting reactant. This simple method ensures a direct comparison against the balanced equation. A crucial point to remember is to avoid a common mistake. The limiting reactant is not simply the one with the smallest mass or the lowest number of moles. It is determined by the stoichiometric ratio. In other words, you must always take the balanced equation into account. Let's work through an example to see this in practice. Here is our first worked example. The question asks us to identify the limiting reactant when 4 moles of sulfur are mixed with 20 moles of fluorine. We are given the balanced chemical equation, which is our essential guide. First, we look at the balanced equation. We can see that 1 mole of sulfur reacts with 3 moles of fluorine. Now, we'll apply our tip and divide the given moles by the coefficients from the equation. For sulfur, we have 4 moles and the coefficient is 1. Dividing 4 by 1 gives us 4. For fluorine, we have 20 moles and the coefficient is 3. Dividing 20 by 3 gives us approximately 6.67. Comparing our results, 4 is smaller than 6.67. Therefore, sulfur is the limiting reactant. This means that all the sulfur will be used up in the reaction, and there will be some fluorine left over, making fluorine the excess reactant. Let's work through another example to solidify the concept. In this problem, the amounts are given in grams, so we'll need to do an extra step first. First and foremost, we must write a balanced equation. The reaction between hydrogen gas and oxygen gas to form water is represented by 2H2 plus O2 yields 2H2O. Second, we must convert the given masses of reactants into moles. To do this, we need the molar masses. The molar mass of hydrogen gas, H2, is approximately 2.02 grams per mole. The molar mass of oxygen gas, O2, is approximately 32,100 grams per mole. The moles of hydrogen are 8.08 grams divided by its molar mass, which gives us 400 moles. The moles of oxygen are 4,800 grams divided by its molar mass, which gives us 150 moles. Now we can determine the limiting reactant using our tip. For hydrogen, we divide its 400 moles by its coefficient of 2, getting 2.0. For oxygen, we divide its 1.50 moles by its coefficient of 1, getting 1.50. Since 150 is smaller than 2 oxygen is the limiting reactant. It will be completely consumed. The question also asks what remains after the reaction. We know all the oxygen is gone. Let's calculate how much hydrogen was used and how much is left over. The stoichiometry tells us that 1 mole of O2 reacts with 2 moles of H2. So, our 150 moles of O2 will react with 2 times 150 moles of H2, which equals 300 moles of hydrogen. We started with 4.1 moles of hydrogen, used 300 moles, leaving us with 1 whole mole of unreacted hydrogen. In terms of mass, that's 1 whole mole times 2.02 grams per mole, or 2.02 grams of excess hydrogen. Finally, we can calculate the amount of product formed, which is water. The stoichiometry between oxygen and water is 1:2. Since we reacted all 1.50 moles of oxygen, we will form 2 times 1.50 moles of water, which is 3 whole moles of water. To summarize, after the reaction, there are no reactants left. We have 2.02 grams of unreacted hydrogen and 300 moles, or approximately 54.0 grams of water product. Now let's turn our attention to percentage yield. While determining the amount of product formed from a limiting reactant is a theoretical calculation, in reality, we don't always get that maximum amount. The theoretical yield is the maximum possible amount of product we could get if all the limiting reactant reacted perfectly, with no losses. The experimental yield, also known as the actual yield, is the quantity of product we actually obtain in the lab. Because experimental yield is almost always less than theoretical yield, we use percentage yield to express the efficiency of a reaction. The formula for percentage yield is the experimental yield divided by the theoretical yield, multiplied by 100%. The key is that both yields must be expressed in the same units, whether grams, moles, or volume. There are several reasons why a yield might be less than 100%. The reaction might be incomplete. Some product could be lost during purification steps, or there could be competing side reactions that form other products instead. Let's work through an example involving percentage yield. This is a common type of problem in IB chemistry. The problem gives us the mass of our starting material, hexane 1-ol, and tells us it is heated with excess phosphoric V acid, which acts as a dehydrating agent to form hex-1-ene and water. We also know the mass of the hex-1-ene that was actually produced, which is our experimental yield. To find the percentage yield, we need the theoretical yield. This means we must calculate the maximum possible mass of hex-1-ene that could be formed. First, we convert the mass of hexane 1-ol to moles using its molar mass. 2040 grams divided by 102.20 grams per mole gives us 0.196 moles. Next, we use the stoichiometry of the balanced equation. The equation shows a 1:1 molar ratio between hexane 1-ol and hex-1-n. So, 0.1196 moles of hexane 1-ol will theoretically produce 0.196 moles of hex-1-ene. Then we convert these theoretical moles of product back into a theoretical mass. We multiply the moles by the molar mass of hex-1-ene, which is approximately 84.16 grams per mole. This gives us a theoretical mass of 16.80 grams. Finally, we have all the pieces to calculate the percentage yield. The percentage yield is the experimental mass, 10.08 grams, divided by the theoretical mass, 16.80 grams, multiplied by 100%. This gives us a percentage yield of 60%. This means that of the maximum possible amount, only 60% was actually produced. Now, at the 10-minute mark, we'd like to extend a special invitation. If you're finding these concepts challenging, or you're striving for top grades in your IB A-level or IGCSE exams, DAR Tutors offers expert personalized tuition. Our tutors are subject specialists who can provide the clarity and guidance you need to succeed. Visit our website or contact us to learn more about how we can help you achieve your academic goals. Let's continue by exploring a concept closely related to green chemistry called atom economy. Unlike percentage yield, which focuses on the mass of the desired product, atom economy focuses on the utilization of all atoms in the reactants. Atom economy is a measure of the efficiency of a reaction based on the mass of the reactants that are incorporated into the desired product. It's calculated by taking the molar mass of the desired product, dividing it by the sum of the molar masses of all reactants, and multiplying by 100. The goal of green chemistry is to design processes that maximize atom economy, ensuring that as many atoms from the starting materials as possible end up in the final useful product, minimizing waste. For example, in the production of ibuprofen, the original 6-step process had an atom economy of only 40%. A newer, more atom-economical synthesis has an astounding 99% atom economy. This means the improved process produces significantly less waste for the same amount of product. Atom economy is a key principle in green chemistry. It's important to remember that it is distinct from percentage yield. Here's a tip. You must write a balanced equation before you can calculate the atom economy. The coefficients are crucial for summing the molar masses of the reactants. Let's work through an example to see this in action. We need to calculate the atom economy for the reaction between copper-2 oxide and sulfuric acid to form copper-2 sulfate and water. First, we write and balance the equation. QO plus H2SO4 yields QSO4 plus H2O. Next, we sum the molar masses of all the reactants. The molar mass of CuO is 79.55 grams per mole, and for H2SO4 is 98.09 grams per mole. Their sum is 177.64 grams. Then we find the molar mass of our desired product, copper-2 sulfate, which is 159.62 grams per mole. Finally, we calculate the atom economy. It's 159.62 divided by 177.64, all multiplied by 100. This reaction has a high atom economy of almost 90%, meaning that most of the atoms from the starting materials end up in the desired product. The only waste product is water. Atom economy is a powerful concept in green chemistry. It helps us evaluate reactions based on their intrinsic efficiency, regardless of how complete the reaction is. It's important to differentiate between atom economy and percentage yield. Atom economy measures the theoretical maximum efficiency of a reaction's stoichiometry. It's a ratio of mass. Percentage yield, however, measures practical efficiency, comparing the actual amount of product obtained to the theoretical amount. As a rule of thumb, a reaction can have a low atom economy but a high percentage yield. For instance, if you produce a tiny amount of product but you collect almost all of it, the yield is high, but the atom economy could still be low if a large amount of other products were also formed. Let's explore another example to demonstrate that a low percentage yield can occur due to competing reactions. Consider the combustion of carbon. In a plentiful supply of oxygen, carbon reacts to form carbon dioxide. However, even with excess oxygen, a small amount of carbon monoxide can also be produced. This second reaction is a competing reaction. Because some of the carbon is diverted to form carbon monoxide, the amount of carbon dioxide produced will be less than what was theoretically expected based on the main reaction alone. This directly lowers the percentage yield of cotadula. Green chemistry is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. Atom economy is one of the key tools to achieve this. One principle of green chemistry is that it is better to prevent waste than to treat or clean waste after it has been produced. This philosophy encourages chemists to create processes that are not only efficient in terms of yield, but also clean in terms of what is left over. By designing reactions with high atom economy, we use raw materials more efficiently and produce less waste. Other green chemistry considerations include using catalysts to speed up reactions and allow them to run at milder temperatures, using safer, renewable solvents, and reducing energy consumption. In some cases, the waste products of a reaction can be used as a raw material for another process. For example, the carbon dioxide byproduct from some industrial processes can be captured and used in carbonated drinks, or as an alternative to strong acids in wastewater treatment, thus creating a circular economy where waste is minimized. Now let's put your knowledge to the test with some IB-style practice questions. Work through them on your own, and then we'll review the fully worked solutions. Question 1 asks you to calculate the atom economy for the production of hydrogen gas from methane and steam, given the balanced equation. Remember the formula for atom economy. Question 2 gives you a reaction and asks you to deduce the limiting reactant when specific masses of magnesium and sulfur are reacted. Question 3 is a multi-part question. First, balance the combustion of chloroethane. Then deduce the limiting reactant when you have 3.0 moles of both chloroethane and oxygen. Finally, calculate the amount of carbon dioxide formed. Question 4 gives you a balanced equation and asks you to calculate the atom economy of titanium produced in the reaction between titanium phosphide chloride and magnesium. It also asks you to explain the relationship between percentage yield and atom economy. Question 5 is an industrial chemistry problem. Given a multi-step process with a 90% yield at each stage, calculate the final mass of sodium hydrogen carbonate you could obtain from 100 kilograms of sodium sulfate. Take a moment to work through these problems. Pause the video here, and we'll go through the solutions together. Welcome back. Let's review the solutions to the practice problems. For question 1, calculating the atom economy for hydrogen gas, we use the formula. The molar mass of the desired product, H2, is 2.02 grams per mole. We have 4 moles of it, so the total mass is R times 2.02, which is 8.08 grams. The sum of the molar masses of the reactants is 16.05 grams per mole for methane, plus 2 times 18.02 for water, which gives a total of 52.117 grams per mole. Plugging these values into the atom economy formula, we get an atom economy of 15.5%. This process produces a lot of carbon dioxide waste. For question 2, identifying the limiting reactant. First, convert the masses to moles using the molar masses of magnesium and sulfur. This gives us 0.2 thousand moles of magnesium and 0.1 thousand moles of sulfur. Since the stoichiometric ratio is 1.1, sulfur is the limiting reactant because we have fewer moles of it. For question 3, the balanced equation for the combustion of chloroethane is 2C2H5Cl. Plus 7O2 yields 4CO2 plus 6H2O plus 2HCl. To find the limiting reactant for 3 moles of each, we divide by the coefficients. For chloroethane, 3 divided by 2 is 1.5. For oxygen, 3 divided by 7 is about 0.43. Oxygen gives the smaller result, so it is the limiting reactant. From the balanced equation, 7 moles of oxygen produce 4 moles of carbon dioxide. So 3.0 moles of our limiting reactant, oxygen, will produce 3.0 moles times 4,7, which is 1.7 moles of carbon dioxide. For question 4, the atom economy for titanium is its molar mass divided by the molar mass of titanium phosphide chloride plus 2 times the molar mass of magnesium, multiplied by 100%. This calculates to 25.1%. The difference, as we discussed, is that percentage yield measures how much product you actually got compared to what you could get, while atom economy is a theoretical measure of how many of the starting atoms are incorporated into the useful product. For the final question, we calculate the overall yield. With a 90% yield for 3 steps, the overall yield is 0.9 times 0.9 times 0.9, which is 72.9%. From the stoichiometry of the overall process, 1 mole of sodium sulfate eventually produces 2 moles of sodium hydrogen carbonate. We calculate the moles of sodium sulfate we start with, multiply by 2 to find the theoretical moles of product, and then convert that to a theoretical mass. Finally, we apply our overall percentage yield. The mass of product obtained is 72.9% of the theoretical mass, which is 86 kilograms. In this video, we've covered the essential quantitative chemistry concepts of limiting reactants, percentage yield, and atom economy. You should now be able to confidently identify the limiting reactant in a reaction and calculate the theoretical yield, experimental yield, and percentage yield. You should also be able to calculate atom economy and appreciate its importance in green chemistry. Understanding these principles is not just about calculations, but about appreciating the efficiency and sustainability of chemical processes. Mastering these topics is key for your success in IB Chemistry HL. Thank you for watching. For more detailed explanations and personalized support, remember to visit DAR Tutors. We're here to help you achieve your full academic potential.